very quickly, I'm just going to turn on the face thingy. There we are. Bam! Alright, there I am. So now we're going to go over to my Google Keep, right over here, and alright, people know what a Turing machine is. Cool. So, this is basically for just computer scientists and mathematician folk. My Turing machine, 7-tuple. We got a non-empty tape, blah blah blah, blank symbol belongs to that. Here. Can I do this? Yep. Alright, so finite non-empty set of alphabet symbols, and blank belongs to it. That's what goes on the tape. Right, and then what else? You got your other symbols that go on the tape, other than blank. And that would include, like, I don't know, 0 or 1 is the quintessential necessary fucking, like, A or B, up or down. You need, like, 2 symbols at least to do anything meaningful, otherwise you just have a tape full of bullshit. Q is a finite non-empty set of states, so that's the set of states your machine can be in. Q0, the initial state, and then F is just your halting states, the states it'll accept on. And then, yeah, your transition function, if it's not defined what your behavior is for the states and the symbols underneath the head, right, then it halts. L and R are special symbols, they go left or right. And, you know, obviously blank is just blank, okay? So let's do something cooler than this, right? So non-deterministic Turing machines can transition to multiple states at a time. That's the difference, right? Non-deterministic Turing machine can transition from one state to multiple states, or be in multiple states at once. That's not something you can do with a computer, because a computer has to be in one fucking state at a time. I'm going to argue that a brain is a non-deterministic Turing machine, functionally, or could be one. A plethora of neurons tied together can be a non-deterministic Turing machine. And here's how I'm going to show you that. This is cool, because we have a machine now, a bunch of neurons. If we could talk to them and ask them meaningful questions, we could do things like break RSA in polynomial time. If you know what that means all of the internet security would be fucking useless. That's not bad. Alright. The set of states Q is where the magic is. So in the set of states Q, you have your state. Here I'm going to like circle this guy. Yeah, let's do this color. Alright, so you circle this motherfucker. That's your state that we're starting in Q current. Q current 0 is just like, you know, this is how you would come up with a set of stuff for your state. Here, I'm going to do something here. Ready? So if you were to basically have states and you wanted to say like, well, maybe there's an infinite number of states I'm going to transition into. So you do a drawing, here we go. So you got Q current, alright? So you'll say like the states I might transition into from here belongs to Q, oops, Q, that's the wrong symbol. Alright, so also belonging to Q is Q current 0, Q current 1, dot, Q current N, alright? So these states also belong to Q. Those are the states you could go to from Q current. Alright, these are the ones you might end up in. Alright? So, you know, then the next one, if you wanted to do it for Q current 0, just be a longer number, right? So, Q current 0, Q current 0, the ones you might end up in are Q current 0, 0, Q current 0, 1, and whatever to your N. Alright? So, interestingly enough, this is cool. So if your Turing machine went on for N moves, and N is infinite, right? If N is a limit, if X is X equals infinity, whatever. Okay, so if that's infinite, then what does this produce? This produces an uncountably infinite set of states that you could transition into. So we're not limiting the states that you could transition to, fucking at all. You could transition into any number of crazy-ass states as long as you transition into fewer than there are neuronal connections. I'll do that. I'll do this explanation really quick. Ready? You got neurons in your brain. Here's a neuron, here's a neuron, here's a neuron, here's a neuron. They're connected like this already in a pattern. That's what they did before you touch them. This is state QC, all right? This is what's already happened. I'm going to use a different color. Here's state QC0. You go for the nearest new connection. QC0. There you go. What about QC1? QC1 is like this. You make a new one. Boom. Right there. All right? What about QC2? QC2. Well, you're not going to connect this one, but you are going to connect that one. There's QC2. Okay? How many average connections does a human neuron have? There's 50 billion neurons in your brain, average, maybe, right? And about 10,000 connections per neuron. So that's 10,000 states you could transition into. That's a good upper bound, you know? So it's not quite a non-deterministic Turing machine, but a computer isn't quite a Turing machine because it doesn't have an infinite tape. You have a limited amount of memory. That is an arbitrary upper bound And we still know that they model computers, Turing machines, model computers, and computers are a limited version of a Turing machine. So a brain is a limited version of a non-deterministic Turing machine when used like this, if it's used like this. Who knows if it's used like this? Nobody fucking knows. We have no idea. But if you had neurons on a platter, and some interesting research about rat neurons used on a platter, 100,000 of them, to navigate a little mouse Android thing, Bluetooth, with a distance sensor. And they navigate a maze pretty well, because we're crazy, and we stimulate them with electrodes if they do the right thing, which makes neurons grow and reinforce each other. We put it in a petri dish full of antibiotics, and that works. So what if we had a brain, and we had electrodes, and we were figuring out a way to do meaningful inputs and outputs? So what if we built an adder with neurons? Is how I would do that. You'd build processor components one at a time with neurons, and you make them work 100% of the time. In other words, you would not do fuzzy math like in a human brain. You would make sure that they're reinforced such that they respond with the actual answer. Make a 4-bit adder with neurons. You can actually draw out how you would do this by hand. If you've ever built an adder with transistors, it's easier with neurons. You can build an adder with neurons, and it's fucking easier than building them with transistors, because logic gates are annoying, and you don't need them if you have an unlimited number of states like this, or nearly unlimited, functionally unlimited. So, human brain, right? So you go up to Qn. So that's going through all these. You do that, and then you finally wind up with Qn. So what if you wanted to do multiple states at once, right? This is what's cool. What if you wanted to do some subset of the states, but only a subset of them, not quite all of them, but not quite none of them, right? So let's reconnect these. So you would do this. You would be like, well, I want to do the first state I was interested in, right up here, as well as Qn and Qn minus 1, and maybe Q2, right? So look, now I'm in that state, which is a combination of those states, all right? I can select the transition, and I can select any number of these states to transition to. And what about the next states? They'll just be off of these, the same way, okay? Recursive definition for changing your states. So this is how you would transition into any set of these states with an arbitrary upper bound being less than your average number of neuronal connections. Because if it's less than the average, you can always fit it into the next set by doing some encoding. If it's easy, if it's like less than the minimum number of connections, or if it's in other words, if your minimum number of connections is 10 instead of 1,000, and you're only ever going to transition into 10 new states from the state you're in, then you're pretty good. And you could engineer something that way, which is really alarming, but you could. You could actually make sure that you had neurons that were connected this way by coaxing them electrically, stimulating them. Then you want to, I don't know, if you're going to do this, you should definitely make sure that in this petri dish there's a shitload of serotonin and dopamine, so that this brain never feels bad doing this shit, because this sounds really, really, really messed up, because we have no idea what it's thinking. We only know what the inputs and outputs are. We don't know what it's thinking, because its thoughts are hidden from us. I also have, interestingly, a mathematics for that. That's kind of cool. Let's do that really quick, and you guys are going to wish I gave you more of it, but I'm not giving you more of it, because I haven't published it, and I want to publish it. Okay, so you have neurons that are connected. Okay, so the math for this is like, if you number these, this is 0, 1, 2, 3, 4, all right? So the math for it is like this. You can write down what a thought is. Neuron 0 goes to a set. Neuron 1, neuron 2, neuron 3, neuron 4, and then you have neuron 1, right, goes to, and you just do it like this. And neuron 0, because it goes right back here, and then nothing happens. That one goes to nothing. And you just do it like that for your set, and you just have sets going to sets, all right? And that's it. That's what a thought is. There might be things on these edges like weights. So like, what's the strength of this connection? Maybe it's like 10. I don't know what that means. Is that the time it takes to traverse it, or is that the reciprocal? Like 1 in 10 is what it takes to traverse it, because it's 10 times stronger. I don't care. You also have things like how much serotonin in this synaptic pathway. Like, I don't know, 50 parts per, I don't care. And like dopamine, like 20, I don't know. And then you just do things like that. You write down the things that matter when you have a function. So you'd have a function like thought function, and it goes on a brain graph, right? So I'm not giving you all the math, but the definition's so long. But like a thought function is a function that's like a transition on this brain, which is a graph. A graph of what? Edges with weights and nodes. The nodes are the neurons. The edges are synaptic pathways, conceptually, with weights like how much serotonin, dopamine, norepinephrine. What is the weight of the connection? And then your function takes all these things into account and tells you what? I mean, what neurons you traverse to, how long it takes to traverse to them, what that means, like, I guess, if there's any value that you assign to it because of their other properties, like serotonin, norepinephrine, dopamine. Things like the weight of the connection tell you something like how long it takes to traverse it, how strong the connection is, blah, blah, blah. So what does that all come out to? Well, you can use that function and the graph together tell you how to think for that brain. That's cool. So if you actually like standardize that in some way, you would know what a thought is and how to reproduce it somewhere else. If you actually had some sort of other function on functions that like made that function into something that worked for the other thing. So if it's in one brain through a set of neurons, then you might have a function on that function that says, okay, how do I take this transition function in this graph and make it into a transition function for a different brain, right? So T prime, B prime, right? So what is this function that takes that and gives you that? If you have B prime already, that's actually interesting, right? That's how you would give somebody else's thought. All right. So T prime, B prime. Let's say you have B prime. You obviously have T and you have B already. We're taking this given, which is crazy. You have T and B, and you say, so what T is equivalent to, what T prime is equivalent to T for B, you know, for B prime. For B prime. Okay? That's cool. I have stuff. I want to publish it. That's it for now.